Picture two very different kinds of bills landing on the same desk. One is a massive one-time invoice for an expedition: vehicles, guides, permits, supplies, insurance. The other is a steady stream of receipts for fuel, snacks, and tolls, as thousands of travelers use the road every day. In AI, training is the expedition. Inference is the road. Training consumes capital up front: compute clusters, data pipelines, weeks of runtime. So it behaves like CAPEX, the kind you plan and amortize. Inference arrives as a relentless operating expense. Every prompt, every chat, every image request demands electricity, memory, and time. So it behaves like OPEX that scales with your users. The surprise is how different the constraints feel once models leave the lab. Tokens become the new unit of cost and throughput. Latency, not peak speed, decides user delight. And the curve that matters is no longer benchmark accuracy. It is cost per served token at your target quality. In the next 20 minutes, we will open the black box of training versus inference, translate the math into money, and show the decisions that shape margins, reliability, and competitive advantage. Before we separate the two, it helps to define them in plain language. Training is how a model learns its general abilities. You feed it vast amounts of data, text, images, code, and adjust its internal parameters until it predicts the next token well. Think of millions of tiny dials being turned to reduce error. Inference is how a trained model is used. A user sends a prompt, the model reads it. Then, token by token, it writes a response. Both tasks run on similar hardware, but their economics diverge. Training is lumpy. You book time on clusters, run for days or weeks, and when you finish, you own a new capability you can reuse. Inference is continuous. Every additional user, every longer context window, every richer output adds to today's bill. Why it matters now is obvious. Generative features are moving from demos into search, office tools, customer support, creative apps, and code assistance. That means companies must answer new questions. How many tokens per user can we afford? What latency keeps people engaged? What model quality is good enough for this task? What happens when demand triples at noon? Governments and enterprises add their own layer: data control, auditability, and uptime targets that sometimes push you to run on your own metal. Every choice shows up in cash flows. Under the hood, training is a pipeline of math shaped by three forces: data scale, model size, and compute bandwidth. Imagine a factory line where each station multiplies matrices, adds biases, and passes activations forward. The pipeline repeats for billions or trillions of tokens. The cost concentrates in the largest phases: pre-training a base model, sometimes fine-tuning on curated data, often an alignment step to make outputs helpful and safe. Hardware matters, here a lot. But the key to predicting cost is understanding that the price you pay is roughly proportional to total floating point operations, and those operations grow with both the number of parameters and the number of tokens you train on. If your cluster is fast but your memory is slow, the chips sit idle waiting for data. That is why high-bandwidth memory and fast interconnects are not luxuries. They are the oxygen of the run. Utilization is the make-or-break metric. A well-tuned training job packs the GPUs with large batches, overlaps communication with computation, and keeps the network busy but not congested. A poorly tuned run wastes days chasing out-of-memory errors or synchronization stalls. The bill is capital-like because when the run ends, the expense ends. You can amortize it across months of product usage, the way a film studio amortizes a big shoot across ticket sales and streaming. Inference flips the picture. The math per token is smaller because you process one small step at a time. Read the prompt, expand the key-value cache, generate the next token, yet the time pressure is far greater. Users feel every 100 milliseconds. Throughput is shaped by a few knobs: the size of the model in memory, the speed of the memory itself, the number of concurrent requests you can batch, and the tokens per second you can produce per chip without blowing up latency. You can imagine a coffee bar. One barista pulling shots one by one will drown at rush hour. A smart line manager batches orders with the same base and adds syrups later. In inference, batching multiple prompts through the same model step increases efficiency, but only if their lengths and settings are compatible. Otherwise, the slowest request drags the whole batch. Memory becomes the first bottleneck because the entire model, or at least its active experts in a mixture of experts design, must reside close to the compute. The second bottleneck is the decoder loop, which must fetch key and value tensors every step. Tricks like quantization, representing weights with fewer bits, speculative decoding, having a small model guess multiple tokens that the big model then verifies, and cache reuse all bend the cost curve. But every token you serve still costs electricity, rent, and opportunity on hardware that could be doing something else. That is why inference is operating expense at heart. The first big decision most teams face is model size versus product quality for a given use case. Bigger usually means better raw capability, but not always better business results. A targeted assistant that drafts emails or summarizes documents may reach good enough on a mid-sized model fine-tuned on your domain, especially if you wrap it in retrieval so it can read your company as knowledge base in real time. Retrieval Augmented Generation, or RAG, is the classic trade. You spend less in training by not baking every fact into the weights, but you spend more per request on search, vector databases, and context handling. The second decision is pre-train versus fine-tune. Pre-training a frontier model is a statement of ambition and budget. Most companies will not do it. Fine-tuning, adapting an existing model to your data and style, is where many of the returns live. It has a smaller capital profile but still benefits from careful planning. How many tokens do you need? Which instruction formats work best? How do you prevent overfitting? The third decision is architecture. Mixture of experts routes tokens through a subset of the network at each step, so you activate fewer parameters per token and save compute. Dense models activate everything every time, which is simpler and sometimes faster at small scales, but costlier at large ones. Quantization is another hinge. Dropping from 16-bit to 8-bit, or even 4-bit weights can cut memory and bandwidth needs dramatically with modest quality loss, but it demands a compatible kernel stack and thorough testing on your tasks. Hardware and hosting choices form a second cluster of turning points. Renting from a cloud gives you elasticity and global reach. Owning gives you control over cost structure if you can keep utilization high. For teams with spiky demand, serverless inference abstracts capacity planning, but charges a premium under the hood. For steady, high-volume workloads, dedicated fleets pay off. Networking and storage design move from background to foreground as soon as your RAG pipeline must hit multiple indexes and data stores under strict time budgets. Caching is low glamour, high leverage. If the same prompts recur, cache the outputs. If long contexts repeat across a conversation, cache the attention keys and values so you do not recompute them. Scheduling matters too. Do you run one large model for everything, or route easy questions to a small, cheap model and escalate the hard ones? That triage pattern, sometimes called model cascading, can cut unit cost without a visible hit to quality when tuned well. A third set of decisions is about reliability and governance. Training failures waste capital, inference failures waste trust. For training, you decide checkpoint frequency, recovery procedures, and validation gates that save you from burning days on a run that diverges. For inference, you design for cold starts, P95 and P99 latencies, and graceful degradation. Observability becomes a product feature. You need token-level metrics, prompt distributions, error traces, and user experience feedback tied to system events. Where data governance is strict, you may keep inference on a private cluster, or at least keep embeddings and logs local. That adds cost in exchange for control. Policy and procurement also weigh in. Export restrictions on certain accelerators, power availability at your sites, and lead times for memory and networking gear can dominate technical preferences. The companies that survive scarcity cycles are the ones that pick strategies that work under constraint, not only under ideal conditions. These choices ripple through the P&L in predictable ways. On the training side, the main question is amortization. How many months of usage will this model support before you need to retrain? That answer depends on your product cadence and on external change. If the world you model, regulations, code libraries, product catalogs, changes quickly, your refresh cycle shortens. If your model is a narrow specialist, it may last longer. In accounting terms, you spread the training bill across the useful life of the model, the same way you spread the cost of a factory machine. On the inference side, unit economics become a game of pennies per thousand tokens. Two levers dominate: tokens consumed per request and tokens generated per second per chip. Reducing the first, through better prompts, shorter contexts, or smarter retrieval, directly cuts cost. Raising the second, increasing throughput, improves both cost and latency as long as you do not smooth over spikes that hurt user experience. Latency targets are not window dressing. They shape batching strategy and hardware utilization. A system tuned for sub-second responses might leave some efficiency on the table compared to one that returns in 3 seconds, but it might win more users and sessions. The right target depends on your use case. Drafting a paragraph tolerates a pause. Real-time code suggestions do not. Pricing models in the market reflect these physics. Some vendors price by tokens, which maps well to inference cost. Others price by the call or by subscription, shifting risk back and forth. Enterprise deals often blend the two with quotas and burst allowances. Margins concentrate where efficiency is compounded. In the model weights you can reuse, in the kernels that squeeze more out of memory, in the orchestration layer that routes workloads to the right place. Winners separate quality from waste. They pay for the capabilities that matter to their users and strip the rest. At scale, even small improvements echo. Shaving 1 cent per thousand tokens can be the difference between a feature that loses money and one that pays for the next round of training. The modern echoes are visible in every category adopting AI. Productivity suites run huge inference fleets behind autocomplete and summarization, dominated by latency and trust. Search engines blend pre-trained models with retrieval and ranking, where efficient context handling matters as much as raw model IQ. Customer support bots live or die by guardrails, escalation pathways, and the ability to ground answers in account data, features that add query time cost but save human minutes. Creative tools rely on image and video diffusion models whose training costs are steep, yet whose inference can be optimized with good sampling strategies and fast upscalers. Code assistants have spiky session-based loads that reward model cascading. Small models handle boilerplate. Big models step in for tricky refactors. Edge inference is a countercurrent. Some applications, on-device translation, audio enhancement, embedded vision, avoid cloud latency and recurring costs by running on local silicon. The trade is power and memory constraints against sovereignty and responsiveness. A balanced portfolio often emerges: heavy training and frontier inference in the cloud, specialized or privacy-sensitive inference at the edge, mid-sized models in private clusters for enterprise workflows. There are limits to the neat CAPEX versus OPEX story. Training is not purely capital. You still pay for power, people, and failed experiments. Inference is not purely operating expense. You often invest in systems that lower its future cost, like better caching, custom kernels, or even your own accelerators. Measuring true cost is tricky. Token counts hide complexity. 1,000 tokens in a short context can be cheaper than 100 tokens appended to a very long context that forces the model to scan vast key-value caches. Quality is multidimensional and user-dependent. What looks worse on a generic benchmark may delight your audience if it speaks your domain or writes in your brand's voice. Long contexts are a double-edged sword. They feel magical, but they carry a linear or superlinear cost if not managed. RAG is not free either. High-quality retrieval pipelines demand good indexing, fresh embeddings, and fast storage systems. Finally, markets move. Efficiency breakthroughs, new attention algorithms, smarter decoding, better quantization arrive quickly. A plan that looks perfect on paper can drift out of date within a quarter. The antidote is instrumentation and humility. From these realities, a practical playbook emerges in plain English. Start by writing down what good means for your use case. Is it factual accuracy? Tone? Speed? Define it before you shop for models. Then set a quality budget in tokens. Decide how much context you really need and enforce it. Most bloat hides in untrimmed prompts and logs. Invest in data. Good fine-tuning data and feedback loops save orders of magnitude later. Treat kernels and compilers as leverage, not as afterthoughts. The team that understands memory bandwidth, attention patterns, and batching will turn last year's hardware into this year's advantage. Design a router that sends easy tasks to cheap paths and reserves your expensive models for hard cases. Cache aggressively and measure hit rates. Where privacy and uptime matter, bring inference closer to your data. Where elasticity matters, lean on the cloud and always instrument the user experience. Track tokens per session, latencies at the 50th, 95th, and 99th percentiles, and correlate dips in quality with system events. If you do these simple things, you position yourself to pay for intelligence where it adds value and to avoid paying for magic you do not need. We began with 2 envelopes, one for the expedition, one for the road. Training and inference will always pull on your budget in different ways. Training asks you to make a bet on a model that pays back over its useful life. Inference demands you manage a living system that breathes with your users. The companies that thrive in this era will be the ones that treat tokens, latency, and reliability as first-class citizens of product design, and that remember the boring parts. Memory, networking, caching. Decide the exciting parts, features, speed, delight. If this episode helped you see where your next dollar of AI spend should go, stay with us. On Incentive Atlas, we break complex money and technology stories into decisions you can act on. Tell me in the comments, where do you feel the pinch today, in the expedition, or on the road, and what should we unpack next so you can ship with confidence?